let's see, homework for today. And then I have exciting news for Jason specifically. All right, so given our semaphore example, and then given our homework from last time, update the homework to use semaphores to do the counting rather than signals. Okay, so if we remember from last time, a semaphore is a way of kind of mutually exclusively blocking something. We talked about this area called the critical section. All right, so the critical section is kind of this chunk of code that we want to protect from being accessed by means of this semaphore. All right. So the idea here is that we're going to have two children just like before. They are going to try to count to 1 to 10 alternating. Since they're not going to be sending signals to each other, they don't actually need to know about each other's process IDs. Instead, they're going to alternate between trying to get into the critical section that does the counting over and over and over again. All right. So let's into the code, and then we will talk about merge sort. All right, so last time we looked at this semaphore, so we can have a named semaphore, so we just called it my bouncer. We went ahead and we created a child process, just a single child process. We said, hey, if you were the child, go ahead and open the semaphore. Say I'm the child, increment the semaphore. That's what post does. So post is the way we grab the semaphore. So this is like us running to the goal, and this is us actually grabbing it. We have something called a race condition. So semaphores attempt to solve this particular problem. I probably mentioned it last time, but let me get it into a slide. Ice condition. Guess that was a Freudian blade thing. So race condition is something that happens on operating systems all the time, and it's actually something that when you're an operating system writer, you basically are defending against all the time. So a race condition occurs when two or more processes try to access the same resource at the same time. This is particularly problematic when that resource can only be used by a single process at a time. Okay, now you could have resources that are that potentially could have more than one process using them at once. We're trying to use real life examples of these types of things. Let's say that there is a big container of I don't know, Hershey's Kisses, or some kind of candy. Okay, now if all of us start running towards that container, it's possible that several of us might be able to use that resource and grab a piece of candy at the same time, even if we both are trying to do it at the same time. So that's a resource that potentially could be shared among multiple people at once. There's going to be finite people to the number of people that can kind of stand around it, but we don't need to go that deep into the analogy. On the other hand, we might say something like a water fountain, or was it a bubbler in Wisconsin, is a single-use resource. So if you and another student are racing towards one of the water fountains on campus, and you both get there at the exact same time, there's going to be kind of this negotiation that's going to take place as to who's going to drink first. You are both going to be drinking from the, especially not during COVID time. Same thing's true when you're driving and two people arrive at a stop sign at the, different stop signs at a four-way intersection at the same time. There's kind of this negotiation to decide who actually gets to go first. All right, so we need to have a similar type of mechanism in our operating systems to handle race conditions when they are a problem. Okay. So in our case here, the SEM post, the way it is handling race conditions is if two processes both try to call SEM post at the exact same time. It probably wouldn't actually be the exact same time, but let's just say it's possible. SEM post operates as an atomic operation. So it means it operates as if it takes a single CPU cycle to accomplish the post. And what post is doing is it is decrementing the semaphore. I'm sorry, it's incrementing the semaphore. Sem close will decrement the semaphore. Okay, so we're going to go ahead and right now we have a single child. They connect to the semaphore. They grab the resource so that they can get into their critical section. Then they relinquish the semaphore. And then in this case, they're also unlinking it. Whereas if we're the parent, they also attach to the semaphore. So they walk up to the bouncer. They then say, okay, I'm going to wait for that resource to be available. So we're not actually mimicking a race condition here. Instead, we are choosing to alternate between the parent. Well, the parent's just going to wait until the child has relinquished that resource. All right, so what we need to do is we need to create two child IDs. So we'll have our first child. If I'm the parent, we're going to go ahead and create a second child. All right, and what do the children do? The children are going to try to count. All right. And then we'll go ahead and just do like an else. No, do I have sys weight up here? Yep. Okay. And that's when the parent will actually exit. All right, so if we are the child, we want to go ahead and connect to the, I'm going to steal this code. We're going to put it up here in a other function. We'll call this guy child. Count function, something like that. We'll paste that code in there. For now, we'll do some modification. All right, so both children here are going to be doing the same thing. Now, we don't necessarily care which child gets to the critical section first, as long as they're going to alternate between each other. All right, so both children will attach to the semaphore. Now they're going to be doing some counting. To do the counting, we're going to need to use some shared memory. So let me go ahead and why didn't they make open and close do opposite things? Yeah, I don't know. For the same reason that they use the kill command to send a message for signals. There's probably a rationale behind it, probably based on some old system call from the earlier days of Unix, like in the 70s or something, but I don't know what it is. Okay, let me go get our let's see, let me save this real quick. Go get our, well, actually I can just grab it from some online resource. I'm gonna have 0 screen real estate on this computer. Because we're going to use shared memory to do our counting. Just waited here twice. All right, so we'll bring that stuff in for our shared memory. I want to use the private example that we had last time. Let me just use it off of our example. I think I gave a link in the homework. Last homework solution. All right, so we had our integer pointer for shared memory. We actually don't need it to be global in our particular case, but we'll burn that bridge here in a minute. So this is where we get the segment ID that all of our players are going to know about here. So we will do that right here at the top of main. So all of our children, as well as the parent, will have access to that single segment ID that was generated from IPC private. For our shared memory, we will go ahead and attach to the shared memory. So whether we are the parent or the child doesn't matter. Actually, what I'm going to do here, I'm going to say SEM-ID. I'll make that guy global as well. That way I can compartmentalize this a little bit. So inside of our child count function, we will attach to our shared memory. We will also effectively attach to our semaphore. If you want to think of those two things as similar, you know, we are grabbing our shared memory that we're going to be flipping back and forth between, and then we are going to go ahead and start using that for our counting, for our back and forth between the children. Okay. So let's just say if we are the child, let's go ahead and get our call in here. Regardless of which child we are, we're going to call the child count function. So if I'm the child here, call the child count function. I already have the sem stuff in there. So let me dump this stuff. If I'm the first child, call the count function. If I'm the second child, call the count function. In either case, the child is going to call the count function. If I'm the parent, then I'm going to sit here and wait for all of my children to finish doing their thing. Okay. So what we want to experiment with here is what happens if two separate children try to post at the same time. So what I'm going to do is we'll go ahead and put the process ID here of this child. We can leave it as the unlinked for right now. That's not going to hurt anything. We're not going to do any of this stuff right now. Good programming practice would probably say that we actually do close and unlink from the semaphore if we are, and actually we're going to say let's do that as soon as possible. So as soon as we get to the parent isn't even using the semaphore here. So the parent's just going to close the semaphore and then unlink it. In fact, actually the parent never opened the semaphore. They actually just got the, they opened it. So they do need to close and unlink since we had everybody. Well, no, they didn't open it. Sorry. Segment ID. Yeah, they didn't actually open it. So the parent doesn't have to do anything related to the semaphore. They're not involved. Only the children opened it because I put it all inside of this function up here. Only if you call child count function will you open the semaphore. All right, so now we can look at this and say, okay, well, probably this child is going to start cooking first because there's going to be a little bit of wait time for that second child to be born and then for them to call their count function. Okay, so that's probably going to be the situation. So we're going to look at what happens with sempost for a binary semaphore. That is a semaphore that only allows a single entity to get into the wait or get into the critical section rather. Okay, then I will say I'm in the critical section. And we'll go ahead and also announce the process ID there, just to prove that the same guy is in the critical section. And then we'll do one more thing after we've closed. We'll say left the critical section. And then this child will die just for right now. We're going to have the children do some counting here in a few minutes, but for right now, we're just going to have them both race to this resource and then prove that they got it. And what we want to see is that the same child gets into the critical section. And while they're in the critical section, before they relinquish it, we don't see another thing. Let's see, that could be a timing thing though, actually, because IO takes a little bit longer. We might just have to believe it. What I'm getting at here is what we're trying to prove is that only one child is in here at a time, which is they can't get past this line right here until they're the only ones allowed in that critical section. Now, what I'm saying is we should see I am the child, I've left the critical section first. The ideal situation would be we see this line and then we see this line before we see this line for the other child. But technically, the amount of time it takes to do IO right here might be longer than the amount of time that between this child closing the semaphore and then the other child getting into the grabbing the semaphore.
I have a question. If you put a sleep function inside the critical section, would that prove that the other person can't get in right away?
Probably. At the very least, I think what you're saying is not unreasonable. So let's sleep for 1 second. And then why don't we announce that we're leaving the critical section before we actually leave? And actually, why don't we put our sleep after that? I think that should prove the point that these two lines, well, does it really? We're still not going to be guaranteed that this line beats the sem close. We should definitely see both of these lines occur for the same child before we see this line occur for the other. Because that proves that we were in the critical section for this guy and that other child blocked right here, trying to add one to the semaphore, trying to grab the resource. All right, so what we're looking at here is the difference between sem post and sem wait. All right, so then we'll go ahead and close. The child, once he exits the critical section, will just announce, okay, I'm out. I've done my thing. I've left the semaphore. Somebody else can use that resource. Both children will go ahead and call that function. And at the end of that function, the code just ends, and which will allow the parent to finish up. Did I not put a segment ID? Where am I at here? Line 23, shared memory, segment ID. Oh, my segment ID is
I had to pass it in as a parameter.
Say this again.
I had to pass it in as a parameter for it to work, but I guess how you're doing it would work too, I think.
Yeah. I'm just going to put it as a global variable. We'll give it value here. Although you wouldn't want to pass in your segment ID for shared memory. Oh, you could. I get what you said. You kept it as an int here, and then you passed it into both of these functions, the two children functions. Yeah.
Yep.
So I'm just making it global so they'll both have access to it. But it's important, as we saw a couple classes ago, that we get our shared memory one time using this IPC private. All right, so I am the child about to approach the bouncer, 1050. I'm in the critical section, 1050, leaving the critical section, 1050, about to approach the bouncer. Now, actually, that is interesting that guy couldn't open. I didn't think sem open blocked. Let's just make sure it runs in the same order multiple times. Yeah, here's our example. What I said before is that the amount of time it takes to do that final IO might be longer than it takes to enter the critical section. What I'm finding surprising here, that it's actually sem open that is blocking. Because 100% of the time, we're not able to open this semaphore. First child's about to approach the bouncer, and not before that first child leaves the critical section does the second child even start approaching the bouncer. That seems to be consistent. About to approach the bouncer, about to approach the bouncer. So what that's telling me is that, oh, and also keep in mind that we're sleeping for a second in there. Although even that, why did that seem like it should have taken, we sleep for like 5 seconds. No, they're both getting into the critical section. So none of them are blocking actually. This just happens to be that that first child is getting it, as opposed to sem wait for the first child. Can't do sem wait for this example. I need to separate it between the two children. Taking an int pause. Say if pause is equal to 0. We'll do a sem post on sem ID. Else. We'll do a sem wait on sem ID. Then do a post. Now I'm having my function take in an integer pause, and I'll pass it a 0 for the first child and a 1 for the second child. So if we're the first child, we'll go ahead and grab the resource. If we're the second child, we'll wait for the first child to leave the first time, then we'll grab the resource. So the first time into the child function, we'll pass in a 0. Second time, we'll pass in a 1. All right, so both of them get in. Both of them start to approach the bouncer right here. The first one gets into the critical section, 1663, announces they're about to leave the critical section. Then they waited, what do I say, 5 seconds? So we got to this line before the next one happened. Then the other child gets into the critical section. So announces he's leaving the critical section. They both eventually spit out they left the critical section. I don't think the way we have it written right now guarantees that these lines will always be the last 2 lines. You're kind of at the mercy of IO being expensive. I don't know if we'll be able to run it and actually have them not be the last 2 lines, especially with the wait. Let's see, leaving, we have left the critical section. In the critical section. Oh, this is actually interesting. We're actually seeing the amount of time IO is taking. This was our actually our second child was able to spit out. He left the critical section, so now he's already out. Whereas the first child never actually got that comment out, because he immediately ended. So this IO thing, this is an interrupt. So we do a context change on the CPU. So it interrupts the CPU to go and do some input output. We then unlink from the semaphore, and if you're either one of the children, you hit the end of the program and you're done. Program's over. Well, what's happening here is, since that child, his program ended before this guy finished. And that's actually not the problem here, because this message to go and print this out had already been sent to the operating system before he died. So even if this process had died, that was still going to get spit out to the screen. But what we've seen as behavior from online GDB is, if the parent of the process dies off, the children stop speaking. So it cuts off everything. So it is kind of interesting that only one of them was able to announce that they left. Yeah, they both got it at that time. Okay. So in any case, we are going to go ahead, and we have our shared memory here. If we were pause 0, and this is our first time through, we want to start our counter. All right, so we're going to go ahead and do something like int. The question we might want to ask here is, we might want to say, if the value that lives in shared memory how do we ask if shared memory has not been initialized? Because this shared memory location is going to have whatever the default value is in that shared memory location. Does that make sense? So it's going to have that default value in there initially. Now, we suspect that default value will be a 0. So we can probably prove that here. If we go ahead and maybe I'm the child in the critical section, and we go ahead and just do a second %d, and then say value at shared memory. We're going to see what the value is of that shared memory before either of the children put any value in there. And we see the initial value is 0, which is convenient for us in this particular case. But you've probably heard me say several times in the past that if you don't want to rely on the default value of variables. If you want it to be a certain value, you make it that certain value. In this particular case, that actually creates a new hardship for us. Let's get it counting first, and then we'll talk more about that hardship. We see it's a 0, so we know we can count off of that. So what we're doing right here in this original control is we're saying, if we are the first child, pause a 0, go ahead and grab the resource. Otherwise, the second child will wait until the first child is done with that resource. No sleeping, nothing special, and then they will grab the resource. Okay, now we want to keep doing this over and over and over again until the count is equal to 10. So while the value in shared memory is less than 10, we want to go, well, we're not going to go equal to, we'll just start with less than 10. So while it's less than 10, doesn't matter which child we are, we're going to do some stuff. If I'm pause 0, I'll go ahead and post. If I'm not pause 0, I'll go ahead and wait. Now, what I'll probably do is I'm going to put this before our while loop. That'll stagger them. So before our while loop, if we're the first child, we'll grab the resource. Otherwise, we will wait for our resource. So now inside of this while loop, we want to go ahead and print out the current value of our, shared memory. So we'll go ahead and we'll maybe use this guy. So I'm the child, I'm in the critical section. Here's my process ID. Here's the current value of shared memory. Then we want to increase the value of shared memory. So we'll add 1 to it. We saw last time that we can't do the plus plus with a pointer, but we can do plus equals 1 like that. All right, so now we're going to have that child give up the shared memory, which will then allow the other child to get in. Other child will then pass this bouncer, grab the resource, come into their while loop, and do their thing. Now, as I have it right now, we have this in a while loop. We saw a similar model last week, where now both children are stuck inside this while loop trying to do their thing. So first child prints out a 0. The 0 becomes a 1. The first child then relinquishes the semaphore, letting the second child in, who reads that a 1 is less than 10. They'll print out a 1 along with the other process ID. And actually, why don't we just we'll show that initially before we put it back into the while loop. Take that out for a second. Get rid of this sleep, get rid of that. Yeah, this is fine for now. So we should see a child do the account. We should see the order of the children. Oh, I guess it's not necessarily, we won't know necessarily which child does the first one. And the child about, oh, because he exits too quickly. So we need to just well, here, do a while one with the children, so they'll never exit. That way it'll be allowed to finish. All right, so first child is a 0, then we count it up to a 1. Fine. So now these children want to keep going back and forth using this semaphore to manage it. Now we're hopefully, I doubt we'll actually accomplish it, but we're hopefully going to be able to produce a race condition here. So now, this is my critical section. I want to do this, relinquish the semaphore, and then I actually want to go ahead and do this stuff again. All right. So if I put it inside of a while loop, like I had before, oh, I gotta close off my thing here. So we're going to say, if I'm a child, I want to keep doing my thing here as long as the value of shared memory is less than or equal to 10. I'm still participating in a count. When I get into this area, I'm going to go ahead and display something, add 1 to it, relinquish the semaphore. And then I'm going to try to get access to that semaphore again. All right, so we initially synchronize right here. If I'm child 0, I'll go ahead and grab it first. Otherwise, I'll wait my turn. Then once we're in here, child in the critical section, we do our addition, we give up, then we wait for the other child to finish, presumably bouncing back and forth without doing any sleeps. Okay, and then we'll leave our while 1 stuck in here for right now. Have it shared memory. Oh, while it's less than or equal to 10, it's immediately less than or equal to 10. So I got to keep going. Well, no, that is what I want to keep doing. As long as shared memory is less than or equal to 10, do all this crap. Close it. Wait again. Post. This child is getting into it. Why did this only run once? We saw both children get in here. We relinquished the semaphore. And then the child decided to wait for the semaphore again. Why isn't it counting? Does anybody see what stupid thing I'm doing?
Did the parent die or something? I doubt it, but I'm just curious.
The parent
And
shouldn't.
that doesn't matter. I had a sleep 10 in mine, and mine's doing the exact same thing.
The parent should not die until both children are dead. The children should be stuck in this while loop. So as long as our shared memory is less than or equal to 10, keep doing all this stuff. We know it started off at 0. We printed it out here, became a 1. We saw it printed out the 1. 1 became the 2. Relinquish the semaphore. Do we need, maybe we need to reopen it. As long as you have a semaphore open, you should be able to just keep using it. We definitely don't have to reopen it. Lose some weight. Let's make sure they're both getting to this line. Possible that one of these, because the thing is ending, it's possible that one of these is actually erroring out.
You do have to reopen it, by the way.
You do have to reopen the semaphore. So you have to get a new.
Yeah, I reopened it after we said close and it works.
That means that is the blocking, or that is the, oh, here, let's do this. I'll just steal this guy. So this is our initial synchronization to make sure they grab the resource in the right order. Then they do their thing. They close. Well, then presumably I'm going to take the weight out then for a second. Because presumably we will not be able to open again until the other one has closed it. Once we've opened, then we can post. That's a very one-sided competition. The other child never. Yes, that's just one child counting all the time. See, the problem with this is the same thing we dealt with shared memory. This SemID, for us to say we want to wait for the SemID becomes problematic because SemID is going to be a new value every single time we open it. So now when I tell one of the children to wait for SemID, they're not waiting for the same SemID that the other child got. So actually, I think we want to do this. It's going to work the same way as our shared memory worked. I presume it's going to. I'm only going to open once, just like I did for shared memory. So everybody will have access to that same SemID. They'll go ahead and attach to the shared memory, but they only use the SemID once. Okay. So I'm not going to reopen it here. You shouldn't have to reopen it. You should have a single SemID. My understanding is you should also not have to wait. You should immediately try to grab the resource again. Although waiting should guarantee the order. I declared a second time. Oh, it's already declared up there. both of those types were actually integer types. Okay, so now we're back to what you said with the, you had to open it again. That would be very bad.
It worked one time when they were alternating, but I haven't gotten it to work since. It's only been one child.
Let me look at terminal. Well, here, we'll do it in a Google search. So sem open. The man page for that. So it opens a name semaphore. Creates a new POSIX semaphore or opens an existing semaphore. Semaphore is identified by a name. Let's print out that sem ID. See what the value we're getting for sem ID is if we do open it multiple times. Another %D. So the third value is going to be the value of sem ID. Oh, I need to, this line has to be here. Okay, it's always getting the same value. So that would say that opening it multiple times is actually okay. Because that sem ID is always the same value. It's complaining that I'm trying to print out a decimal, but it's actually a sem type, which is a it's a sem type pointer. So actually, do I need to do star sem ID? I could just turn it back into an int. See our sem type. Does it tell us in here what sem type is? Sem type is just an integer type. We don't get sem type from there. This guy's saying unsigned char. It's definitely not a memory address. So I think we're, and this is just a warning, right? So I think it is the same sem ID every single time, but that does not tell us why it's always the same child. So we do offset. Clearly, the first child is grabbing it. The second child is waiting for him to finish. First child gets in here, starts his count, closes, reopens. And I think at that point, he's waiting on himself. I shouldn't, if I take the weight out of there. Oh, actually, he is waiting on himself because he's waiting for it to be available. The first child is finishing their count. It's always the same PID. They're counting up to 10. The second child is still waiting right here for the first child to finish. Let me do this. You know what sum open does? Maybe the issue is that we're closing it. We'll talk about thread safety when we talk about threads. So some post increments the thing, so that grabs it. The other guy waits. We're dealing with binary semaphores that only go up to 1. So they wouldn't be able to both get in at the same time with the post. Sem open not working the way I want it to work. Some close do. Closes the name semaphore returned by some. We should only have to open it once. We should only have to close it when we're completely done using it. Otherwise, we're posting and waiting. Okay, unlink means that it's no longer a thing. I think we definitely want the parent to do that. Function calls. So some post unlocks it, some wait locks it. So some waits what actually gives up. So it decrements the semaphore pointed to by a sem. Okay. I think it's a naming convention issue. So this guy will unlock the semaphore initially. It's actually the second child. I think this is our they're both going to try to lock it. So I actually want to so grab the resource. That should try to lock it. I don't think it's going to matter whether we're pause 0 or pause 1 here. We'll just create the raise condition. Like I said, I wanted to try to prove. They'll lock it. They'll do their thing. Then they'll post, unlock it. We should let the other guy then get in to lock it, go back and forth, back and forth. Just take out that sem-ID thing there. So I think that is stopping us. We need them both to open it locally. We definitely don't want to open it every time, but maybe you need an individual PID to open it once. And then to eventually close it. We don't have to close in our example here. Okay, so I think we do still need to do our synchronization. Pause is equal to 0 if we're the first child. Then we will say sem post, sem ID. That'll initially unlock it, which then will let that first child lock it. First child will do their thing. Oh, I want to take that guy out. I didn't want that in there before. I also don't want to close it. So it's possible that I actually had let me go back to what I was doing. So we do need to initially unlock it. So post unlocks, wait locks. This is an increment. This is a decrement. Semaphores are atomic integers for counting, and we're doing a binary semaphore, which should just go 0 or 1. So this should take it to a 1. This should take it back to a 0, grabbing the resource. Why is it always the same child? There's the other dude. He finally got in there. So is the while loop happening too quickly? And this is when we never unlock it. Okay, yeah, so that makes sense. Neither child can lock it because it was never initially unlocked. The resource, when it's first available, needs to be unlocked. So now we lock it, getting the resource, do our stuff, unlock it, which should then allow the next person to come in and lock it. Now the other child is in this while loop, and he's blocked right here on the sem wait. But he should immediately get unblocked as soon as this guy relinquishes it. So the question is why isn't he? We do have both children calling this function, right? Here's the first child after the fork. There's a second child after the fork. They both call the same function. They're passing whether they're 0 or 1, which child they are. Child 0 unlocks the semaphore. They both go ahead and open the semaphore, although I don't think you actually have to do it here. I think we could have done it out someplace else, but let's say this isn't going to hurt anything. Both children open the semaphore once. First child will unlock it, and then immediately grab it. Do something, and then unlock it again. And that other child's only getting in at the end. Didn't even get in that time. Why are they not alternating? I'm gonna have to fiddle with this, I guess. This is not working the way I expect it to be working. So clearly we're not doing merge sort yet. Let's see. I know we're out of time. Let me just read what Jason said here. I didn't see it. Solution I found is at the very end of the parent, put wait null, and then also sleep 1. So you think that the parent is actually dying off before that second child can do its thing? If I put sleep 10 there, that should be good enough. No, that didn't seem to make a difference. All right, I'll fiddle with this. No homework over the weekend, obviously. You need to have working code. In my mind, this should be working. And I don't believe that it's going to be an online compiler thing. It has to be something that I'm misunderstanding about wait and post. Semaphores are definitely integers. This is definitely a decrement. This is definitely an increment. So somehow the other child isn't even trying to mess with it. All right, so I'm actually gonna keep playing with it this afternoon. So while I wait for a message from Blade. So I'll look for me to post something on Slack, kind of explaining what was going on here. I'm confident I'll have some solution for you. Okay, well, I guess, sorry, we don't have a working solution there, whatever. So I guess I'll see everybody on Tuesday.